Hello everybody, welcome to day 2 of L'Hopital. In the last video, we talked about how L'Hopital's rule helps us to deal with indeterminate forms, but very specifically, we talked about 0 over 0 and infinity over infinity, because technically, those are the only two indeterminate forms that L'Hopital applies to. If you don't have a 0 over 0 or infinity over infinity, you have no business doing L'Hopital. You may stumble on a right answer if you do it anyway, but you're probably going to get a wrong answer, and AP is probably going to make sure of that. So what I want to do today is talk to you about the other 5, because there are 7 indeterminate forms. Let me see here. My computer's going to work for me. There we go. All right. Okay, so here's the 7. I think we talked about these, a few of them briefly in the beginning of the year in chapter 2. 0 over 0 and infinity over infinity, obviously, we already addressed. Today, I want to address the rest of these with you. Now, AP does not address all of these. For the most part, AP is going to stick to one of these first 3. It is possible we could see infinity minus infinity, but usually not. And then these exponential ones, I'm going to show you real quickly what we do with them, just so you know. But it's nothing that is going to come up for us on the AP. They don't require us to do the exponential ones. I probably don't have to tell you that those are the biggest pains in the butt. Okay, so let's talk about these first 2, and then we'll quick talk about the other 3. All right. Infinity times 0. This is an indeterminate form. I like to think of it as, I'm sorry. I think if you multiply anything by infinity, it's either going to be infinity or 0, depending on if it was greater than 1 or less than 1. But theoretically, if you multiply anything by 0, it should be 0, right? So there's some question here. I always prove it to people by doing some, there's a thing called the dragon fractal, where you take a strip of paper. Let's say it has a length of, I don't know, 1 unit. Right? And you take that piece of paper, I'm going to draw a piece of paper, and you cut it in half, right? So you started with 1 piece, and it had a length of 1, right? For a total length of 1 unit. Now we've cut it in half, so I have 2 pieces that each have a length of 1/2, but I still have a total length of 1. Okay. If you then go back in and cut these in half, now I have 4 pieces. They're each 1/4 long. I still have a total length of 1 though, right? If I keep doing this, my number of pieces is eventually going to go to infinity. The length per piece is eventually going to approach 0 or 1 over infinity, right? This is approaching 0. But my total length is still going to be 1. So somehow, in this case, infinity times 0 is 1. And I could prove to you that it's 7 too if I started with a piece of paper that's 7 units long. Or 22 if I started with a piece of paper that's 22 units long. So that's just kind of a real quick example of why this is indeterminate. Not that you need to know why it's indeterminate, frankly. All you really need to know is that it is indeterminate. Right? So 0 times infinity, indeterminate. Here's the problem, it's not rational. Right? And L'Hopital only deals with rational functions. So for example, I have the limit as x approaches infinity of x times the sine of 1 over x. If I try to evaluate this as I go to infinity, x is going to be infinity, and then the sine of 1 over infinity, also known as the sine of 0, that's going to give me a 0. That's a problem. Okay. The answer to the problem, the solution to this problem, is algebra. All you have to do is rewrite this as rational. There's a real easy way to do that. Anytime there's an x out front, okay, you just rewrite it like this. Instead of multiplying by x, you divide by 1 over x. That's the same thing algebraically. Now think about that for a minute. If you have x and you're dividing it by 1/2, is that not the same as multiplying by 2? It sure is, right? The invert and multiply thing. So we're literally doing that in a reverse order. And it seems kind of strange to do because you're kind of unsimplifying it, but that's what we have to do because I need it to be rational in order to use L'Hopital. So once I have it like this, now that I'm reevaluating, I evaluate now, I'm going to get a 0 on the top and also a 0 on the bottom. So it's bad news that it's indeterminate, but great news because I get to use L'Hopital, right? And now I can use L'Hopital. So this is just a real quick, if you see an infinity times 0, find a way to rewrite it as a fraction. Like I said, there's usually an x that you can just invert and multiply. You could, if you wanted to get real cute, rewrite the trig function in the denominator, right? Like 1 over sinus cosecant. So you could rewrite that as x times, or x divided by the cosecant. Does anybody want to do that? You could, right? I usually just play with the power of x. Okay. Once you've got it as 0 over 0, it's a real quick L'Hopital, right? I'm not going to write out the whole statement because I know you don't like it when my videos are long. But remember, you have to say, since this function is equal to 0 and this function is equal to 0, L'Hopital states that, here's my new limit. The limit as x approaches infinity of the derivative of sinus cosine 1 over x, chain rule, and then in the denominator, you get that, and boom, those cancel, and all you end up evaluating is the cosine of 1 over x, which is the cosine of 0, which is 1. And you can see in your graph here that as you go to infinity, you've got an asymptote at 1. Oops, sorry. You got an asymptote at 1 here. Okay, so that's that kind of indeterminate form. This next one, infinity minus infinity. Also indeterminate but not rational. Also a pain in the dupa. Here's why. I have 2 rational functions. I need it to be 1 rational function. Remember algebra 2? Remember common denominators? That's what this is going to require you to do. Right? I need this written as 1 fraction. So to do that, I have to find a common denominator. My common denominator in this case is just going to be the combination of those 2. Right? So I'm going to have the ln of x times x minus 1. And then my new numerator will be x minus 1 minus the ln of x. Right? So again, I haven't done any calculus. That's just an algebra rewrite. And when I now evaluate this as x equals 1, on top you get 1 minus 1 minus 0. On the bottom you get 0 times 0. Again, I just went from having one kind of indeterminate form to another kind of indeterminate form. But this is great news because this indeterminate form I can work with. That indeterminate form I can do L'Hopital on. I can't L'Hopital this. I can L'Hopital this. Now this is a fun one because this L'Hopital is a little bit interesting. So let's do this one. If I L'Hopital this, on the top I'm going to get what? 1 minus 1 over x. On the bottom I have a product rule. So I have the ln of x times the derivative of x minus 1, which is just 1, plus x minus 1 times the derivative of ln of x, or 1 over x. So if you evaluate that at 1, you get 0 on the top, 0, 0. You get 0 on the bottom. It's still indeterminate. Right? So this is one of the ones where you have to L'Hopital a second time. So if we L'Hopital this a second time, on top I get positive 1 over x squared. On the bottom I get 1 over x. I'm going to do a quick rewrite here so I don't have to use a product rule. If you FOIL this out, this right here, if you FOIL this out, you get 1 minus 1 over x. I really don't want to have to do a product rule, so I'm going to do a little algebra instead. So when I take the derivative of 1 minus 1 over x, I get another plus 1 over x squared. And when you evaluate that at 1, you get 1 over 2, which you can clearly, well, maybe not so clearly see, but you have an asymptote there coming at 1/2. And that's our answer. So this one's kind of a pain. Again, you have to do this algebra rewrite. Do not do L'Hopital on these individually. That is a big fat no. First of all, these individually are not indeterminate. It's their difference that makes them indeterminate. rewrite it so that it gives you a 0 over 0. Then you can L'Hopital twice. Okay. All right, so those are those two. So just like to review really quickly, if you see, you can only use it on 0 over 0 and infinity over infinity. If you see an infinity times 0, rewrite that thing as a quotient. If you see an infinity minus infinity, you're going to have to rewrite it as one fraction. So you're going to have to find the common denominator. As I said before, this one is way more common than this one. They say to focus on 0 over 0, infinity over infinity, and infinity times 0. They say to focus on those ones, but they never say they won't give us this one. All right, last three. These guys. Okay, we could talk for days about why these are indeterminate. Perhaps we'll do that one day. Okay, here's the deal. In order to get at these, I need to turn this exponential function into either a 0 over a 0 or an infinity over infinity. So the first thing that we have to do to make that happen is get rid of the exponential piece. Do you hear what's coming? Okay, so first thing we're going to do is take the ln of the function. Right. So I know what you're thinking. You can't just take the natural log of a function. Yeah, I can. Right. It's kind of like you can do anything to an equation as long as you do it to both sides. Right. So if I have a function or a limit is equal to a number. If I take the natural log of the limit, what that's going to result in is the natural log of my answer, and I can fix that in the end. Okay, so the first thing we're going to do is use the natural log to get the exponent down. Okay, rewrite it like logarithmic differentiation. Once it's down, you're probably going to have an infinity times 0 type situation or something like that. Then you can use that, rewrite it as a quotient. So I'm taking it from the exponential form that I don't want. By taking the natural log, you can rewrite it as a quotient and then hopefully use L'Hopital. Now, as I said before, once you use L'Hopital, the answer that you get isn't your answer per se, it's the natural log of your answer because you took the limit of the natural log of the function, not of the function itself. Right? So what we have to do in the very last step is exponentiate our answer to undo the fact that we took the log. So in other words, in the end, I don't have my answer, I have the natural log of my answer. So to undo that, I go, okay, well, I'm going to take that and raise e to it because the e and the natural log are going to cancel each other and I'll just get what my answer should have been. Okay. These are a pain. Okay. So first we take the natural log to rewrite it. Then we do all the L'Hopital stuff that we would normally be able to do. And then to undo the fact that we took the natural log, we exponentiate in the end. Okay. Again, AP doesn't make us do this. I just wanted to talk to you briefly about what you would do. So let's look at one real quick. Notice this is only a one-sided limit. How fun that is. Okay. So we can see here we're going to have a 0 to the 0, which is indeterminate. So I am going to take the ln. Now what I do in this case is I write a little ln there so that I'm reminding myself what I've done. So if I take the ln of this function, I can rewrite it as x ln of x. I now have, let's see, a 0 times a negative infinity. That's indeterminate. But I can fix that by rewriting it like this. That's still a problem, right? Because now I have infinity over infinity. But now I can L'Hopital. So even though I'm mad, I'm kind of happy. So when you L'Hopital this, let's see, I get 1 over x over negative 1 over x squared. So algebraically, let's see, let's simplify that because I'm going to get infinity over infinity if I just go right away. But that's 1 over x times x squared over negative 1, right? So that's just negative x. So now when I approach 0, I'm going to get 0. Okay, so the answer to this limit is 0. But you can look at this graph and see that as you approach 0, that's not the answer, right? It's not, because I took the natural log. So I have to exponentiate my answer. My answer is actually e to that, which is 1. What? It works. Okay, again, that's not something you're going to have to do, but that is 3 of the 7 indeterminate forms, how they have to be addressed. So you may see that when you go to your next level of calc. So I just wanted to make sure it wasn't completely foreign to you. Okay, so any questions you have, put them in the end of this video. We will practice with L'Hopital tomorrow, and then we're going to have a quick quiz on this stuff before we move into integration. All right, we'll see you later.